put your questions into the chat box addressed to all, and we will have time at the end for Q&A. And with that, I turn it over to JC.
Hello, everyone. So this is part 2 of the series. Last time we talked about the solution and how it addressed the medical devices supply chain space. Today is more diving into the underlying sort of system that's underneath that solution and how it works. This is going to be a bit of a accumulation of experiences that we have accumulated, some lessons that we've learned, some mistakes, and in general how we've addressed the complexity of the system. Just hold on a second. I have it. Okay. So the outline is as follows. I'll start with a summary of the solution as it was described in part 1. That was last week. Next, I'll talk about the complexity of the system that's underneath that solution. And then we'll dive into 3 main being talking about the reliability of the system, next about the security of the system, and then finally about the evolution of information in the system. The largest section is going to be the reliability. The security section, the evolution of information is also a bit. So what's the problem? First, let's environment. Again, we talked about it last week. This is a physician preference items environment. It's a subset of consumable medical devices, high cost that could go up to $20,000 per item. They constitute quite a large chunk of total hospital supply expenses, both in terms of percentage as well as in terms of the mix is complex. It consists as well as consigned products still owned by manufacturers. The availability of these products is critical to patient care. They have expiration issues. Hospitals don't have good inventory management systems. There's lack of dedicated staff and so on. That's the environment, and the problems that arise from it are in 3 categories: patient safety issues, financial problems, and operational problems. The details of these are in the previous presentation, so I won't dive into them. But rather, I'm going to dive into what the solution is, and there's going to be one more slide as to what the solution is. The solution that we've implemented is a series of RFID nodes across the provide end-to-end visibility to the product lifecycle. It goes through distribution centers and the trunk stock of sales reps and ends finally when the products are consumed at the patient. And these RFID nodes are running on a SaaS platform, software as a service, that's shared between suppliers and between providers, which are the hospitals. So that being the solution, where does complexity come in? First, let's talk about SaaS. So SaaS, or software as a service, just very briefly, I'm sure you know what it is, but it's a software that's the internet. It's essentially running in the cloud, and individuals or enterprises don't have to install their own instance of it. They run it in the cloud. There are 3 types of multi-tenancy, i.e. 3 types of ways tenants could sit on a shared the same SaaS platform. The first one is the simplest one. It's separate databases, where every tenant or customer have their own database in which they have their own data. The second type of multi-tenancy is a shared database, but separate schema. So you have a single database for all the tenants, but each tenant have their own schema or data structure, if you will. And finally, the third one, which is the more complex one, is a shared database, but also shared schema. This is where all the data is sitting in the same database, in the same schema, and the logic has to be put on that schema to sort of divide the information between tenants. In addition to that, the solution that we have implemented is actually a shared schema solution, but it has actually a bit more sort of characteristics that increase its complexity. It's actually also a selectively shared data solution. in the sense that the data of the hospitals and the suppliers, etc., is in the same schema, but hospitals and suppliers share some of their data to provide visibility to these medical devices in that schema. In addition, it's an enterprise SaaS as opposed to a consumer SaaS, which adds the complexity of business relationships between the solution provider and the enterprise that's purchasing the system. And on top of the SaaS solution, as I described above, is the network of geographically distributed RFID nodes. So this becomes essentially a combination of a SaaS platform and a series of nodes distributed geographically around the world, and that constitutes the system. Just a quick briefing of what the nodes are. They're essentially a series of RFID cabinets. These are smart cabinets that can read their content. So you plug them into the wall. They have a computer in them. And they act as a network node. It's also a series of RFID stations to do transactions, as well as RFID-enabled mobile devices such as iPhones and iPads, with sales reps who are traveling and doing mobile RFID transactions. So the result essentially is a network that looks as follows. It's one SaaS platform with two types of tenants, hospital tenants and supplier tenants, and multiple instances of each tenant, running in dozens of countries with thousands of these RFID nodes, transacting billions of RFID tags per year, or reading billions of RFID tags per year. That, and overlaid on top of it, are, depending on the countries and the tenants and the business that we're in, which is healthcare, a series of regulatory and standards bodies that impose regulation, such as FCC, FDA, HIPAA, Joint Commission, and so on. So that's what the network looks like. And the rest of the presentation, I'll be talking about components of this network, but this should give you an idea of the baseline system. The focus today is going to be as follows. We're going to focus on three systems challenges in that network. We're going to focus on security at all levels of the network, at the SaaS level, at the sort of communication level, as well as at the nodes level. We're going to focus on reliability and uptime. And we're going to focus on information and how to get valuable information for a network that's collecting lots of data. Again, the point of view of the rest of the slide deck is on our systems approach. It's on our experience, so our systems approach to it, the implementation that we've done, mistakes that we've made, lessons that we've learned. So, sometimes I'll give you recommendations on what to do. Sometimes I'll tell you what mistakes that we've done. And at the end, please feel free to ask me, any questions, and I'll answer as best as I can. So let's dive into the topics of focus. The first one being reliability. So why is it important? The context is that it's a mission-critical system in the healthcare space. How does it get used? And that influences, how important is reliability. The system is being used on a daily basis to document product uses to patients for clinical documentation. It's being used by inventory managers to order product overnight for a scheduled procedure to a patient the next day. It's being used by a sales rep who just drove an hour and took a flight for an hour, took a 2-hour drive to arrive to a hospital to do an audit on his iPad. Again, it's being used by a distribution center at the end of the quarter, shipping the last shipments for revenue recognition at the end of the quarter. So, and hopefully this shows the mission criticality of the system. So then, as we look at reliability of such a system, we break it into two components. The first component is the SaaS platform reliability. This is the reliability of the SaaS infrastructure, of the servers, of the software, etc. And the second component is the reliability of the network. And by network, I mean the collection of nodes that are reporting to the SaaS platform. So I'm going to first dive into the SaaS platform reliability in a series of slides, and then dive into the network reliability after that. The SaaS platform reliability, the stack is essentially the reliability of the infrastructure, such as the data center, the offsite tape storage center, and so on, the hardware that sits on top of that in terms of servers and load balancers and whatnot, the enabling software that's on top of that, such as Oracle in your operating system, etc. And then on top of all of that is the developed software, which is the application that you develop as an organization. The following are areas of interest in terms of reliability. The first one is around processes and mistakes or bugs. Processes in such an environment are extremely important in order to minimize mistakes, whether it be at the software development level in terms of a quality management standard that you develop against, or in terms of minimizing errors of what to deploy, when to deploy it, and the requirements for establishing SaaS change management and customer notification processes so that you don't deploy a new version without informing the customer, so they log in the next morning and they have no idea what happened. And what's also important to minimize mistakes is establishing a software release process that accounts for the geographical span of your customers. So when we first started, we were running in the East Coast and we would release at 9 p.m. Then we start having West Coast customers and we said, okay, we'll do it at midnight. Then we expand to Europe and then all of a sudden you can't do it at night, so you have to do it on the weekends. And, and as you expand, for example, into other geographical locations, if you go to the MENA region, etc., the weekends are also different between regions. So you have to take that into consideration as you start thinking about what's your software release process and how do you do it and when do you do it. Another area of importance, and I feel it's given very, very little attention, is data backup and data recovery. And actually the backup is given quite a bit of attention, but it's the recovery that's lagging. Most people think of this as backup. Most people feel safe when they know that the data is backed up. But the backup turns out to be the relatively easy part. The difficult part is actually the data recovery and understanding what your processes are and establishing processes around when to recover data, what to recover, under what conditions, how do you test that the data has been recovered properly, and so on. So a very big recommendation here to establish procedures for the backup and, more importantly, the recovery, and to actually periodically practice these procedures, and specifically the data recovery procedures, in order to do two things. A, you need to verify that your data is being backed up. And B, you need to practice and be able to do it in a timely manner so that when it's needed, you know how to execute it rapidly. It's another area of concern, again, around reliability and something that should be given attention is this area of redundancy and failure recovery. So, you can run whatever you like for a system failure analysis mechanism, and out of it, most probably you'll implement redundancy at some critical nodes. They'll be at firewalls, servers, load balancers, and so on. This, one type of redundancy is this N+1 redundancy that I described here, which is, N is the number of systems you need, and you always have +1 system, more than you need. And the organization should establish procedures to test failure, make sure that you can, truly, if there's a failure, you can go from N+1 to N. But more importantly, which is not given focus, is testing that the system can actually run at N. So as an example, let's say you have 3 servers and each one of them is at 90% capacity. If one goes down, true, you have 2 servers left, but all of a sudden you have to get to 270% capacity, which you can't do. So in this way, you'll be in trouble. So you want to make sure that the system can run at N, and also when the failure is mitigated, know how to recover the system back to an N+1 state. Again, in instances like these, you're usually under pressure, under the gun, trying to bring the system back up and running. And the last thing you want to do is be designing what to do at that point in time. The design should be done way ahead of time, and this should be purely execution time. Another area that I'd like to talk about is disaster recovery. So this is where you have a system and you're planning for what if a disaster hits the area where your servers are running, essentially. And you want to move the system from a primary site and run it off of a secondary site. This tends to be one of the most expensive costs that you will have because it requires additional infrastructure in different locations, staff for this infrastructure, procedures around it, licenses for software, and so on. I don't know what the right time to implement is. There is no right time. It depends on what the organization. It depends on the organization. What needs to be taken into consideration is the financial situation of the organization, requirements of customers, requirements of regulatory bodies, and the appetite of the organization for risk. But one thing is for sure that once a disaster recovery site is deployed, it can certainly be used for other purposes. So it does not have to sit idle. It can always be used for non-mission critical applications, such as business intelligence, read-only, and so on. And upon failure, this is where you drop your non-mission critical applications and you use it as it becomes essentially your primary site. Another recommendation is, again, practicing disaster recovery. Again, you don't want to be designing it on disaster. You want to have designed it way ahead of time and just be executing on disaster. Another area to talk about are third-party providers. We all use third-party providers in terms of data centers, off-site tape backup sites, outsourced developments, contractor DBAs, and so on. Your reliability is very tightly tied to your third-party providers. Their certifications, their internal policies and procedures directly affect the reliability of your system. And essentially, they become an extension of your procedures and policies, both practically as well as if you get audited. So for an audit on reliability, the auditors most probably will dive into who your vendors are and what are they doing. And these have to be acceptable to your auditors. And speaking of auditing, although this is not only directly related to liability, but I wanted to mention that in the healthcare space, you will get audited, re-audited, re-re-audited. You'd be audited by customers, customer representatives, regulatory bodies, agencies, etc., for various things such as quality, data security, reliability. One thing is, we've learned a lot from these audits. They're scary, they're painful, but after every audit, we emerge as a better organization because we've learned from every audit and we implemented changes to our policies and procedures, and we've only become better organizations to audit. So although they are time-consuming, they should be sort of welcomed as an opportunity to advance. And with that, I end the talk about the SaaS platform reliability. Again, I gave sort of a few bits and pieces here and there of things that we've done to address system issues from that point of view. Next, we dive into network reliability. And this is, again, talking about now the nodes that are running on the network. So what are the characteristics of these nodes? Again, these are the RFID cabinets, the transaction systems, and the mobile devices. These nodes are electromechanical nodes. They're electromechanical devices with embedded firmware and software in them. In some instances, they are actually mobile devices. They run in an environment where we have a distributed geographical span. So across multiple states, multiple countries, thousands of them. They're generally located behind firewalls, except for the mobile devices. Behind these firewalls, there are strict guidelines that control the network for both the medical device suppliers as well as the hospitals. Contractually, as an organization, this is an important bit of information as to why we worry about this network, because contractually, as an organization, we take on the full support and maintenance for these nodes. So that's a perspective that you should keep in mind as we talk about this. And given that, you want to minimize travel, because travel is very expensive if you have to fly to location in order to fix a problem. So first, let's focus on the node, and then we'll start from there and then move to the network. So the function requirements of a node are as follows. First, it has to achieve its primary business functionality, be it read RFID tags or read transactions or read inventory, whatever that is. But in addition to that, from a reliability point of view, a node has to do three things. It has to be monitorable, it has to be controllable, and it has to be upgradable, i.e. we need to know what's going on with it and if it has any issues. We need to be able to tell it what to do, start it, stop it, etc., or make it recover from problems. And we need to be able to upgrade its software in order to either enhance the software or fix any bugs that we might find. So now let's take this monitoring, controlling, and upgrading and see how it moves from looking at a single node to the network evolving. So over time, the network evolves, and whether you're working at the node level or at the network level, you still need to do the three functions: monitor, control, and upgrade. The difference is that at the node level, the complexity is generally very low, while at the network level, it's actually quite high. And therefore, while early on at the network level, one could get by having the engineering group or the group that developed the software monitor and control and upgrade this network, when the network grows, it requires a dedicated network operations group whose sole purpose is making sure that this network is up and running. As far as implementing in the software this monitoring and control, etc., the implementation can be done at the node level early on and at the network level over time as the network grows. However, the system itself of how to do this has to be built, designed early on with the network in mind. Because once the network evolves and the nodes are out there, it's tough to redesign the system and transform these nodes that are out there from being individual nodes to being monitorable as a network. So again, although you might not need to implement it at the beginning as a network, and you might not need to build an organization that deals with it as a network early on, from a design point of view, very early on, it needs to be thought of as a network that will span geographies and span multiple instances. So let's dive into these three components: monitoring, controlling, and upgrading. A few words on each. So monitoring is detecting hardware, firmware, and software statuses. Again, the complexity increases with scale and with collected data. So the more nodes on the network, the more data that's being collected, the more complex this monitoring becomes. Early on, monitoring could be a report-driven mechanism where one could go to a report, search for data, and find out what's going on. As the network evolves, this must change into an alert-driven mechanism where some automated system goes through messages, throws away all the ones that are not relevant, and then only alerts on the ones that are relevant. And hopefully over time, that can grow into a predictive alerting, where one could use historical data to predict alerts before they happen. So essentially, it moves from a problem happens, I go look for it, to I get alerted on a problem that has happened, to I get alerted on a problem before it happens. And when I hit that last stage of getting alerted on problems before they happen, this is where I can start making my network more reliable, but and also as well reduce the cost of doing that, because I can plan ahead before failures occur. From the point of view of control, it's the ability to perform actions on the nodes of the network. The design must account for the deployment locations of these nodes. These nodes are located in different physical locations, behind firewalls, with network restrictions, IT regulations. As an example, they're sitting behind the firewall of a hospital or a medical device supplier, or on the mobile device of a sales rep on a cellular network. So it's very important to design the proper communication protocol. So early on, you might not have the list of functionalities that should be controllable, However, the communication protocol should be designed from the beginning to take into consideration all of the restrictions and not violate them. And then the solution, the system could evolve into a system where monitoring and controlling are happening together. So it can evolve into an automated control-based system, control based on network alerts. The system essentially will self-recover from failures. So your alerts could then feed into automated control, and the node itself can detect its status, recover from it, still inform that it has recovered, but recovered on its own. And again, this is where cost goes down, because you don't need to scale your back-end resources in your operational environment sort of proportionally to the size of the network. And finally, the last topic on reliability, it's around upgrades. Nodes have to and will be upgraded over time for bug fixes or for functionality. Upgrade is a very important functionality, but it's the most dangerous functionality, and it has to be designed extremely carefully. Because the upgrade functionality, of all functionalities, it has the capability of crashing the system and making it non-upgradable. So if you think of introducing any other bug in the system, as long as you have the upgrade functionality, you can upgrade it remotely and fix that bug. But if you introduce a bug into the upgrade functionality, that system is now unrecoverable unless you physically fly there. We've done some of these mistakes early on, and we've learned from some of these mistakes. So it's sort of a big word of caution on that front. That ends the reliability focus area. Now I'm going to jump into the security part. So security. There are many headlines out there. Dark reading is a website I like to follow. You can read, from dark reading, you can read headlines like this all the time. 2 major breaches caused by loss of physical media. Misplaced CD containing data on 29,000 patients. XYZ loses data for some 79,000 employees. These headlines are out there. They result in financial losses to the organization. They result in legal problems, and they certainly result in customers' perception problems. We all remember them. We all remember that we've read them in headlines and so on. Data security, as the system is being built, has to be designed into it. It cannot be added as an afterthought. And the reason for that is that it's not just a technology problem. And looking at it from a technology point of view, it's not enough. It has to be embedded in the company culture. You have to have employee buy-in into security. Employees have to understand why it's important. It has to be in the organizational structure, and I'll talk about that in a bit. There have to be policies and procedures around it, training around security, audits around security, and so on. And therefore, so when I talk about it be designed in the system, it's not only the technical system that's being deployed, but rather the system of organization and people and company and technology. So first, let's start by defining it. Most people think of data security as confidentiality. So as long as my data hasn't been breached and it's confidential, then it's secure. There's a wider definition of data security that actually involves data availability and data integrity. So it's not enough that the data is confidential. It's also important that I have access to the data and that it hasn't been modified when I had access to it, i.e., I have the data, nobody else has the data that shouldn't have access to it, and this data is correct. And so that's the more comprehensive definition of data security that a system design should address. First and foremost, in an environment such as the one I described in the healthcare space, assigning the responsibility at the senior management level is critical. The organization should assign a chief security officer whose responsibility is to ensure data security. This is definitely not a problem or responsibility of an IT department. Quite often I hear that, and that's definitely not the case. It's definitely, and it's at the level of the entire organization. It spans the entire company. Next, the organization should choose a security framework. There are many influences as to which security framework should be chosen. There are geographical influences such as countries and their rules and regulations between the US, Europe, Asia, and so on. There are various regulatory bodies, both within the countries or within different industries, such as HIPAA, EU, FDA, you name it. There are multiple customers that have their own needs in terms of security, because then they themselves are regulated. So they have their own internal needs as well as they have regulatory needs that are imposed on them. On the other hand, there's one organization, which is the organization that's implementing the system, and the assumption is with limited resources. So one thing that works for us, and it could work for others, is picking one framework, picking the most comprehensive security framework, and implementing it well, and then extending it when needed for other regulatory needs. So frameworks tend to have lots of overlap between them. Implementing several security frameworks end to end might end up being wasting a lot of time. And so the advice here is to actually go after one and extend it as needed and when needed. Next, we need to understand the threats. So it's threats to data. So the first question is, what is the data? So what's the data that we're dealing with? Not every bit of data requires the same level of security as critical data. So what's the data that you want to make secure? The second question is, where is the data? It can be in two places. The data could be sitting at rest, or it could be in transmission, in transit. At rest, it could be sitting in databases. It could be sitting on backup tapes. It could be sitting on offsite storage, printed materials, laptops, and so on. Or it could be in transmission. It could be viewed on a web browser, on a thumb drive in your pocket while you're on a plane. An email, a phone call is a form of transmitted data. A verbal chat is a form of transmitted data. So first thing you do is once you've understood what data you want to protect, understand where is that data as you're analyzing the threats. Next, we go back to our definition of security and say, okay, so how will integrity of this data be compromised? How will its confidentiality be compromised? And how will its availability be compromised? And by what threats? So threats can come in various forms. You can have physical threats as well as logical threats. For example, you can have a disk drive stolen or a message intercepted. They could be malicious or not intentional. You could have a hacker that hacks into your database, or your IT person leaves a disk on the loading dock. They could be internal or external. It could be your internal staff, maliciously or unintentionally, that compromises your data. Or it could be external people. It could be hackers, it could be, and so on. So again, understanding where's your data, what can happen to this data, and by what mechanisms is very important. From here on, you'd implement your own threat risk analysis process. There are various ways of doing it. Sort of pick your own based on the industry, based on what you're familiar with, and so on and so forth. At the end, you'll end up with a series of risks. And what I feel is that it's very important to be able to prioritize and understand what to focus on, because the risks, after you look at them, will be overwhelming. So where do you focus? I'm proposing here a mechanism to help in this prioritization exercise. It's essentially looking at risk in terms of impact and probability. So what's the probability that this might happen? High probability or low probability? And what's the impact if it happens? There's high impact, low impact. And the focus of the organization ends up being on the high risks, which are high impact, high probability, then moving to medium risks, which are high impact, low probability, or high probability, low impact, and finally, if time permits, on the low impact, low probability. So again, it's very important to prioritize and tackle them in order of priority. But once this has happened, what do you do? How do you look at threats? There's a common tendency to focus on prevention, which is not bad, but it's out there, and it's bad if you only focus on prevention. People tend to think of security threats in terms of prevention, using HTTPS, protecting with username and password, encrypted, very difficult to guess password, change it every 30 days, locking workstation, and so on. However, I like this as a better definition of how to think of security in terms of a Deming quality cycle. Essentially, you prevent, but you also, while you're preventing, you also try to detect breaches. If you find breaches, you contain them to limit their damage, and then you create corrective actions so that they don't happen again. So again, it's a cycle of preventing, correcting, preventing, detecting, containing, and correcting. And actually, there's a statement by the HIPAA security regulations that states that it says implement policies and procedures to prevent, detect, contain, and correct security violations. So then what's the outcome? So once this has been implemented, I'm giving you here an outcome of what we have implemented as an organization to give you a flavor of how security sort of gets ingrained in the entire organization. Again, this is a sampling. These are not all our policies and procedures, but this is where we ended up with. On the HR side, for example, we ended up with security training procedures for new employees, as well as retraining for after a certain period. We've implemented employee termination policy that ensures that employees don't leave with access to data that should be secure, with sanction policy in case of violations, intentional or non-intentional. On the operations and customer service side, we ended up with security incident policy and an incident response procedure where customer service and operations understand what the policy is around security incident, and should an incident happen, what's the notification procedure and the response procedure to these incidents, as well as access control policies that instruct them who to give access to and who not to give access to, and to what data. We ended up with IT policies and procedures, such as email policy of what to put and what not to put in emails, who to not to send them to, etc. Workstation use policies around locking desktops and so on. Antivirus policy, device and media control policy. We end up also with network operations policies, such as change management procedure, so that if you're deploying a new software, paying attention to what its impact is on security. Usage monitoring procedure that looks on the back-end network and sees if there are any attacks on your network and tries to take actions against these attacks. And finally, on the software side, where you have your standard transmission security policy, where you make sure that your software talks in an encrypted manner, that you do user authentication, and so on and so forth. So again, it's this. Again, this is just a sample of it, but it's this kind of thinking and these types of policies and procedures across the entire organization that truly up the level of data security within your offering. And in addition to that, very important to conduct periodic external audits. Again, they are time-consuming, they are sometimes painful, but these external audits give you always a different perspective, and they are always a mechanism by which you can improve as an organization. And with that, I end the second section, of focus, which is system security, and I dive into the last one, which is the evolution of information. And again, this is a smaller section than the other, and so this is the problem we're dealing with. And by the way, this one is more of a internal experience that we have gone through. So I'm sort of sharing that experience and the learning from that experience and trying to generalize it a bit. So the problem is that we provide lots of information, as you know, as a system, as well as various systems that a typical user has to interact with. These systems provide tons of information. If we look at a typical user in a hospital, for example, hospitals have scarce resources. These resources are overworked. Their primary objective is patient care, not looking at systems here and there. They have to inevitably deal with various systems, though, and they have limited time to spend on each system. So that has to be taken into consideration as we give them information. So, and the idea here is to start moving from reporting to tasks. So, you know, sort of years ago, there was this talk about moving from data to information, data into information. I feel that has happened, right? So data has been moved to information. There's many solutions to that. Now the question is, how do we start within information, move from information to action? So when you give a person sort of a report with large sets of data, they look at it and they're just sort of not sure what to look for. Then you evolve the system to start giving them an alert, and they see the alert and they get it. They're like, oh, I see the alert, but what do I do about it? And in an ideal way, you give them actually a task, and you say, this is exactly what you should do, and that's where they get it. And given the small attention span that they have and time to spend on your system, they can go in, see what they need to do, go do it, and get out of the system as fast as possible. So we're evolving from a series of very rich, extremely rich data to a list of things to do, where the user does them, check, 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 and they get out. Again, this is for the typical type of user that we're dealing with, but it tends to be sort of, you know, your typical user in a healthcare setting. So our experience is as follows. We first started sort of a few years ago with this type of information. So we would give the user all the information. So we say, okay, this is all the information I have. Go through it, find what you are looking for, and decide what to do about it. Again, the information was rich. The nodes were collecting lots of this data. It was all there, and the user had to find what they're looking for in it and then make a decision. An example of that is, you know, a typical inventory report that we had. So we had an inventory report of our physician preference items. A report like this would be maybe 2,000 or 3,000 rows. We had a column that showed the expiration date. And, you know, the user could see it and sort on expiration and decide what to do about products based on when they were going to expire. From there, we moved one level up, and we said, okay, so the system evolved into a system that says, okay, this is the information that you are looking for. You don't have to look for everything. This is what you're looking for information, but you make the decision. You decide what to do about it. And the actual example of that was a report that looked like this, where we would alert the user on expired products or on products, for example, that will expire in the next X days. The user clicks on this alert, sees the products, looks at them, and decides what to do about them. The problem is that, you know, you look at products that will expire in the next, let's say, 7 days, and you're thinking, well, are they going to get used from now to the next 7 days or not? I can maybe take some actions, but I actually don't know what to do. I just know that, you know, now I have the data in front of me. And finally, the system evolved into a system that tells you this is what you should do. And this targets the user that logs into the system, clicks a few buttons, again, gets out of it, and spends as little time as possible on the system. And that's our goal. And that evolved into something that looked like this. So now what we're doing is we combine inventory information with usage information. We run some predictive algorithms, and we alert the users on which products will definitely expire regardless when they will expire. It might be next year, it might be next month, it might be 2 years from now. Based on the usage pattern and based on what you have on hand, these products will definitely expire. And that is actionable information because these products need to be swapped out. With that, I end this presentation. I hope it was informative. Again, it was a accumulation of some experiences that we have and learnings that we got along the way. And if you have any questions, please let me know.
Hi, now we'll begin the Q&A period. If anyone has any questions for Jean-Claude, please feel free to enter them in the chat window addressed to everyone, and I will read them aloud. We do have this ability, so please feel free to chime in if you have any questions.
Okay, well, I know JC has a meeting he needs to get to, so if you have any questions, please send them directly to JC or to me, lslavin, L-S-L-A-V-I-N @mit.edu. We will have the slides posted within a day or so, as well as a recording of this seminar, this webinar, excuse me. I want to thank you all for coming. JC, we'd like to thank you for participating. Our next webinar will be on October 17th, and details will be sent out in about 1 to 2 weeks. Thanks very much.
Fantastic. Thanks.